Let us solve a question on constrained optimization. The question is, find the optimal units of goods Q1 and Q2 given the utility function of a consumer is U is equal to under root Q1 times Q2, and price of good Q1 is $50 and price of good 2 is $20, and income of the consumer is 5,000. We will also learn how to find out the marginal utility of money, that is the value of lambda. We will solve this question using Lagrange's multiplier method, or Lagrange's what we call the method. So what we have been given? We have been given the utility function of the consumer. So our endeavor will be to maximize the utility that the consumer gets from consuming the two goods, that is Q1 times Q2. Okay, we want to maximize the utility of the consumer subject to the budget constraint. And what will be the budget constraint? That will be the price of good price of good Q1 times units of good Q1 consumed by the consumer plus price of Q2 times units of Q2 consumed by the consumer or purchased by the consumer, and it should be equal to the income of the consumer. So specifically it will be, so P1 is 50, so we have 50 Q1 plus we have 20, the price of P2 times Q2 should be equal to the income of the consumer, which is 5,000 here. Okay, graphically what exactly is meant by this stuff? Let me draw the simple graph here. So let us say we have Q1 on the horizontal axis, Q2 on the vertical axis. Okay, with the given budget line, or with the given budget, and let's draw the budget line, it will look like this. So with the given budget, consumer wants to maximize his utility. Okay, that is graphically it means the consumer wants to reach to the highest possible indifference curve. Okay, so there can be one indifference curve like this, IC1. There can be another indifference curve which is IC2, and consumer's endeavor will be to maximize his utility, and it will happen at a point where the slope of the budget line is exactly equal to the slope of the indifference curve. Okay, so this point will be the optimal point. But we will solve this question using Lagrange's method. For that, what we need to do, so we use here Lagrange's method. First, this is our given budget constraint. We set it equal to 0. That means we write it like this: 5,000 minus 50 Q1 minus 20 Q2 should be equal to 0. First step is to set the budget constraint equal to 0. Second step is to multiply both sides by lambda. Okay, if I multiply this by lambda, so it will 0 times lambda will be equal to 0. Third step will be to form the Lagrange's function. So let's denote it by L. So Lagrange's function is formed by adding the given utility function, what we call the objective function, and the result budget constraint. That is, we add this utility function, and let me write it in this fashion: Q1 raised power upon 1 upon 2 times Q2 raised power 1 upon 2, plus we add this resulting constraint, that is lambda times 500 minus 50 Q1 minus 20 Q2. Okay, now to find out the optimal units of good Q1 and Q2 and the value of the lambda, what we need to do, we need to partially differentiate this Lagrange's function with respect to Q1, Q2 and lambda, set them equal to 0 simultaneously. Okay, so that means L subscript 1, let us assume L subscript 1 means the partial derivative of this function with respect to Q1. Okay, so derivative of Q1 raised power 1 upon 2 is 1 upon 2 will become coefficient, then we have Q1 and exponent will be subtracted by 1, so 1 upon 2 minus 1 is minus 1 upon 2. Q2 will remain same because we are taking the derivatives with respect to Q1 partially, and derivative of Q1 in this term will be 1. We are left with minus 50 times lambda, so we will get minus 50 times lambda, and we set it equal to 0. Similarly, we take the partials with respect to Q2, that is the partial derivative of the given function with respect to Q2. This time we take the derivative with respect to Q2, so the exponent of Q2 becomes coefficient. Then we have Q2 and then first we have the Q1 raised power 1 upon 2, and Q2 will be equal to 1 upon 2 minus 1, which becomes minus 1 upon 2. And here the derivative of a constant is 0, derivative of Q1 will be 0 because we are taking partials with respect to Q2, and derivative of Q2 in the last term will be 1, so we are left with minus 20 times lambda, and we set it equal to 0. Similarly, we need to take the partial with respect to lambda. Okay, since no lambda is involved in the first term, derivative of the lambda will be 1. We are left with 5000 minus 50 Q1 minus 20 Q2, and we set it equal to 0. Now to save the space here, what will I do? Let us transpose this. Okay, how do I put it? So since this is equal to 0, if I transpose this to RHS, it will become plus 50 lambda. Okay, so I am just skipping this step, so removing this equality sign. Similarly, if I transpose minus 20 lambda, it will become plus 20 lambda. So it is like this. Let us say this is equation first, this is equation second. Now what will we do? We divide equation first by equation second. So we will get here, for this, let me rub this. So we have 1 upon 2 Q1 raised power minus 1 upon 2 times Q2 1 upon 2 divided by dividing LHS with LHS and RHS by RHS. Here we have 1 upon 2 Q1 raised power 1 upon 2 times Q2 raised power minus 1 upon 2 should be equal to, so here we have 50 lambda, here we have 20 lambda. Lambda and lambda gets cancelled, 0 0 gets cancelled here, and here 1 upon 2 gets cancelled. Okay, if we transpose Q1 raised power minus 1 upon 2 to, and let me show it here, let us transpose this Q2 to numerator, so it will get multiplied. So we have Q2 raised power 1 upon 2 times Q2 raised power 1 upon 2. When I transpose this Q2 to numerator, it gets multiplied, but its exponent sign changes, so it is minus 1 upon 2, it becomes plus 1 upon 2. Similarly, I transpose this term to denominator, so first we have Q1 raised power 1 upon 2 times Q1 raised power, it is minus 1 upon 2, it becomes plus 1 upon 2, and it should be equal to 5 upon 2. Okay, so bases are same here, we can add the exponents, so 1 upon 2 becomes 1, so we have Q2 upon Q1 is equal to 5 upon 2, which gives us Q2 will be equal to 5 upon 2. Transposing this, it becomes Q1. Okay, now we plug this value in this equation, in third equation, or we can also plug the value here. Okay, it is one and the same thing. Let's plug it in this equation, it will be more simple here. So plugging the value of Q2 in this equation, we have 50 Q1 plus 20. In place of Q2, we have 5 upon 2 Q1 is equal to 5000. So 2 1s are 2, 10s are 20, 5 10s are 50. We get 50 Q1 plus 50 Q1 is equal to 5000. Okay, so it is 50 plus 50 is 100 Q1. So we have 100 Q1 is equal to 5000. Dividing both sides by 100. So here this gets cancelled. We are left with Q1 will be equal to 50. That means consumer will consume 50 units of we get 2 1s are 2 tens are, so 50 plus 50 is 100. Okay, so consumer will consume 50 units of good 1. To find out the optimal quantity of good 2, plug the value of Q1 is equal to 50 in this equation, so we will get 5 upon 2 times 50, so it gives us Q1 will be equal to 2 ones are 2, 25s are, so we will get Q2 is equal to 25 into 5 is 125. So consumer will consume 125 units of good 2. Okay, what about the marginal utility of money, what we call the shadow price? That is the interpretation of the lambda. And let me rub this out now. Now we need to find out the value of lambda. Okay, so we can find out the value of lambda by substituting the value of optimal value of Q1 and Q2 into either equation 1 or equation 2. Let us put it in equation 1. That gives us 1 upon 2. Okay, then let me write Q2 first. So we have Q2 raised power 1 upon 2. Transposing this to denominator, it becomes Q1 raised power 1 upon 2 should be equal to 50 lambda. So let's write it here like this, which implies 1 upon 2. So we have Q2 upon Q1 whole raised power 1 upon 2 should be equal to 50 lambda, or 1 upon 2 Q2 upon Q1 means 125 upon 50. 1 upon 2 should be equal to 50 lambda, or lambda is equal to, transposing this 50, it gets multiplied, rather divided, so 50 into 2 is 100. So 125 upon 50, it is 5 upon 2, 1 upon 2 raised power 1 upon 2. That gives us the value of the lambda is equal to 1 upon 100 times 5 upon 2, it will come out to be 1.58. Solving further, we will get lambda will be equal to 0.02 rounded off to the nearest second decimal. This lambda tells us, we also call it the marginal utility of money. It simply tells us how does our utility change if there is change in the constant of the constraint. Okay, so what exactly is meant by this? So marginal utility of money, or what we call the shadow price, it shows us how will the utility of the consumer change if the constant of the constraint changes. What is the constant of the constraint? We have the budget here. Okay, so it simply tells how will the utility change if there is change in the budget by 1 unit. That is, since we got the value of lambda is equal to 0.02, its interpretation will be that if what we call if the income increases by $1, okay, utility of the consumer will increase by 0.02 utilities. Okay, so the essence or the meaning of the what we call marginal utility of money, or the value of lambda, tells us how will our utility change when there is change in the constant of the constraint, that is the budget constraint. So here it means if income increases by increases by $1, so utility of the consumer will increase by 0.02 utilities. Okay, I hope I make myself clear in this video and you find out this video helpful. Thank you.